introduction of the chemical education material study.
In tornadoes, houses can blow down because the pressure on the outside of the funnel is very high. Or the house can explode into the rapidly rotating funnel. Gaseous pressure drives this plane forward, while a difference in air pressure between the bottom and top of the wing keeps the plane aloft. How can these pressures be interpreted in terms of molecular behavior? Airplanes are not the only massive objects which remain aloft in the atmosphere. Clouds, which are made up of water droplets, may also weigh many tons. Can molecular behavior explain how the water droplets in the clouds remain aloft? Here is a closer look at a portion of a cloud as viewed through a microscope. The random movement of the cloud droplets is called Brownian motion, after the scientist who first studied it. Something must be jostling these droplets. Here is an object jostling about in much the same way as Robert Brown saw droplets moving in 1827. Turning up the lights shows this object is being hit randomly by many small marbles moving rapidly in all directions. In the same way, molecular collisions account for the erratic motion of cloud droplets. Since the force of these collisions between molecules and droplets is large compared to the pull of gravity, the cloud droplets do not fall. Properties of pressure will be explored more quantitatively now with Professor Campbell.
Pressure in general can be interpreted in terms of random molecular collisions. And pressure differences, as in the airplane, can arise when more molecules per second strike one surface of an object than strike the other surface. We can study the behavior of gases in a pictorial fashion in this machine. Marbles are placed in it, and a vibrating disc at the bottom drives them in a vertical direction. They can strike on the bottom of this piston, which is attached to a gauge. When the machine is operating with only a few spheres in it, we notice that the gauge swings back and forth unsteadily. This is the result of the small number of random collisions per unit of time. With more marbles in the machine, the number of collisions per unit of time should be greater. The gauge reading should be higher. The pressure is higher. Now let's try a quantitative experiment with a real gas. We shall use this equipment. These bulbs contain carbon dioxide gas. They are connected through this stopcock, which is sealed off from the atmosphere. With the stopcock open, the pressure in the two containers is the same, half an atmosphere. Since so many molecules are striking each gauge per second, the pressure readings are steady.
Avogadro's law says that equal volumes of gas contain equal numbers of molecules when pressure and temperature are the same. Thus, when two bulbs have equal volumes at the same temperature and the same pressure, each bulb also has an equal amount of molecules of carbon dioxide.
Now, what will happen to the pressure if we transfer all of the molecules into one bulb? This bulb, for example, thus doubling the number of molecules in it. Well, here's one way to do it. We close the stopcock first, then take some liquid nitrogen and place it around the tip of the bulb.
The pressure in the right bulb drops. The carbon dioxide solidifies on the cold inner surface. Mechanical gauges tend to stick. Tapping produces correct readings. The pressure drops to zero because almost no molecules of gas are present. Opening the stopcock allows carbon dioxide molecules that were in the left bulb to move into the right bulb. These molecules also solidify. The pressure in the whole system drops to zero. Again, tapping helps.
All the molecules are now in this bulb. I'll close the stopcock. Remove the liquid nitrogen and replace it with water at room temperature. The solid will now vaporize into gas, and the pressure rises.
The solid has all evaporated and come back to room temperature. The pressure is now 1 atmosphere, twice what it was when there were half as many molecules in the bulb. By opening the stopcock, the relationship between pressure and the number of molecules can be checked. The pressure drops to half an atmosphere as the molecules redistribute equally between the two bulbs.
These and many other experiments show us that pressure is caused by molecular collisions. Changing the number of molecular collisions changes the pressure. We have studied the effect on pressure of changing the number of molecules in a fixed volume. Let's now study the effect of temperature on pressure.
Temperature is commonly referred to in degrees Celsius. Many scientists use degrees centigrade. The numbers and symbols are the same.
In order to study the effect of temperature, we shall need a substance that remains a gas at low temperatures. From this table, we can see that helium boils at minus 269 degrees centigrade. Let's use it. It should not condense as did our carbon dioxide earlier. We have placed helium in this flask at 1 atmosphere pressure. Let's immerse it in boiling water.
When the flask is immersed in boiling water, the volume and the number of molecules remain constant, but the pressure changes. The pressure is 1.24 atmospheres at 100 degrees. The bulb is now placed in melting ice.
And while it sits, record the data from the boiling water. At 100 degrees centigrade, we got a point here. Our gas was helium. Now let's record the data from the melting ice.
The pressure in melting ice is 0.93 atmospheres. The container is taken out and put into a dry ice acetone slush, whose temperature is minus 79 degrees Celsius. Again, while it sits, Professor Campbell records the data.
At 0 degrees, we got a point here.
Checking on the dry ice, the pressure at minus 79 degrees is found to be 0.67 atmospheres. Liquid nitrogen is minus 196 degrees.
For dry ice, we got a point at 0.67 atmospheres.
Liquid nitrogen at minus 196 degrees Celsius is 0.27 atmospheres. The helium remains gaseous as expected.
Thus, the data for liquid nitrogen give us a point here at 0.27 atmospheres. Now let's try passing a straight line through these points. We see that within experimental error, The line goes through all the points. Furthermore, were we to repeat the experiment with other gases starting at the same pressure, we would find that all gases give data which fit on this line. Perhaps you would like to use these data to get a value for absolute zero.
Here are the data. You may want to stop the projector and use the data to calculate absolute zero. Extrapolation of the data indicates that at zero pressure, the temperature would be minus 280 plus or minus 10 degrees Celsius. This point is called absolute zero, which is the temperature at which molecular motion ceases. The accepted value for absolute zero temperature is minus 273 degrees Celsius, which is within the uncertainty of extrapolation. The absolute temperature scale is expressed in degrees Kelvin, where all numerical values are 273 degrees higher than the corresponding Celsius scale. When temperatures are expressed on an absolute scale, it is found that for a constant amount of gas, at constant volume, the pressure is proportional to the absolute temperature. What does this mean in terms of molecular collisions? Perhaps the marble machine will give a useful interpretation. It has already been shown that pressure changes when the number of marbles changes. Changing the velocity of the marbles also changes the pressure. Could it be that temperature affects gas pressure because temperature affects molecular velocity?
In fact, since the pressures of all gases behave alike at varying temperature, perhaps the velocity of all gases is the same at any given temperature. We can explore this possibility experimentally. Here we have a simple apparatus which will give us further information. The 4 tubes have been filled with carbon dioxide gas. The pressure is kept constant by this tall column of liquid.
A yoke is used to turn all of the stopcocks simultaneously. When the stopcocks are opened, the molecules of trapped gas can strike the foils. In the center of each foil is a tiny hole, so small as to be almost invisible to the naked eye. When the molecules strike the hole, they escape, and the volume of trapped gas decreases. The rate of escape can be determined by the rate at which the liquid rises in the calibrated tubes. Since conditions are the same in each tube, the escape rate should be the same, and the liquid level should rise at the same rate in all the tubes, if all the tiny holes are the same size. All the levels have risen the same amount. The holes are indeed the same size. Here the experiment is repeated using 4 different gases. The tubes are now filled with equal pressures of hydrogen, oxygen, carbon dioxide, and sulfur hexafluoride. The gases are made to escape simultaneously, but the liquid rises at different rates. The experiment will be stopped when 1 unit of the slowest gas has escaped. Reading the bottom of each meniscus ensures consistent measuring of the volumes of escaped gas. 1 volume of sulfur hexafluoride has escaped, and 1.9 of carbon dioxide. 1.0, 1.9. For oxygen, 2.3. And for hydrogen, 8.7. 8.7. Are the rates of escape related to the molecular velocities of these gases? A quick review of the experiment. The pressures in each tube were the same, so were the temperatures. Thus, according to Avogadro's law, each tube originally contained the same number of molecules. Yet different numbers of molecules struck the holes and escaped from each tube. Since more hydrogen molecules escaped, they must have struck and gone through the hole more rapidly. Their molecular velocity must have been higher than the molecular velocity of the other gases. In fact, since over 8 times as many hydrogen molecules escaped as sulfur hexafluoride, the hydrogen velocity must be over 8 times greater.
In the same way, the molecular velocity of carbon dioxide is 1.9 times that of sulfur hexafluoride, and the molecular velocity of oxygen 2.3 times that of sulfur hexafluoride. Let's search for regularities among these velocities, some factor which correlates with them. For example, we notice that hydrogen and oxygen are diatomic, carbon dioxide triatomic, and sulfur hexafluoride contains 7 atoms per molecule. Yet these do not correlate well with velocities, as we can see from looking at the fact that hydrogen and oxygen each contain 2 atoms per molecule, but differ greatly in velocity. In the same way, shape and size do not correlate well with velocities. Hydrogen and oxygen have very similar shapes and sizes, but they differ greatly in velocities. On the other hand, carbon dioxide and sulfur hexafluoride are not greatly different in velocity, but there is a considerable difference in their shape and size. What about molecular weights? The molecular weights are 2, 32, 44, and 146. As the molecular weights increase, the molecular velocities decrease. Do we have a regularity here?
The molecular weights versus velocity are plotted on a graph. The points lie on a smooth curve. In fact, data for all gases at this temperature would lie on the same curve. There is indeed a relationship between molecular velocity and molecular weight. Further examination of these data would show that they fit the equation m times v squared equals c. Molecular weight times molecular velocity squared equals a constant at constant temperature. The marble machine will provide a clarifying analogy. The machine has been modified to include 2 escape tubes. There is a hole in this side which can be opened so the marbles can escape. There are several hundred marbles in each tube, but each of the marbles in the left side weighs much more than each of the marbles in the right side. So the volume contains the same number of marbles, but the masses are different. When the pressures are made to be the same, and the volumes and the number of marbles the same, then, according to Avogadro's law, the effective temperature will be the same, just as with the 4 gases. The marbles are allowed to start their escape. More of the lighter marbles have escaped than the heavier marbles. This is an analogy of how light molecular weight gases escape faster than heavier molecular weight gases. That is, at the same temperature, lighter molecules have a higher velocity than heavier molecules.
Now, what about changing the temperature? We collected our data at room temperature. If we repeat the escape experiment at different temperatures, we obtain these relative velocities. Notice that as the temperature rises, the molecular velocities always rise. Now, from separate experiments, we know that the molecular velocity of oxygen is about 48,000 centimeters per second at room temperature. Using this fact and our experimental data, we can calculate actual values for mv squared for each gas. Notice that at each temperature, the values are constant within experimental error. The average value here is 4.6, here 6.8, and here 8.6, all times 10 to the 10th. If we divide these average values of mv squared by the corresponding value of the absolute temperature, the resulting values of mv squared over T are almost constant. Thus, the relationship between molecular weight, molecular velocity, and absolute temperature is given by the equation mv squared equals a constant times the absolute temperature.
Thus, the molecular model does give a picture of pressure in terms of molecular collisions. The number of collisions depends on the number of molecules per unit of volume and their molecular velocity. Lowering the temperature decreases the molecular velocity, which decreases the pressure. At any given temperature, lighter molecules have a higher velocity.
Finally, the relationship between molecular mass, molecular velocity, and absolute temperature is given by this expression. Any change in the absolute temperature causes a change in the molecular velocity.